I'm here to talk to you today about dead time. Dead time is when you have a transportation lag that's really big and you have to be able to model it somehow, because if you don't, it's going to cause error in your data. So I don't know if you know what that means. I'm sure you guys do, but just cover a little bit more in detail. It's whenever you have you measure a variable over here, and then by the time you read it, it's changed. The variable has changed. So it'd be like if you put a thermometer somewhere and you read it and you get the readout and it's 7 degrees, but by the time you get the readout, it's actually like 9 degrees at that point. That creates a transportation lag, which is not good when you're trying to model it. Some real-world examples would be like, so you have a thermocouple, but it's like wrapped in some crazy glass or something to keep it protected under crazy conditions. By the time it makes its way through all the glass and stuff, the heat on the outside might actually be different. And so there's a real-world case. Another case is if you have a flow meter, or just not a flow meter, like another like a thermometer, like way down a pipe, like 10 feet down a pipe from where you're changing the variable or trying to make a set point. So if you're reading it down there, you're changing it 10 feet from it, then it's going to take 10 feet for it to flow, or it's going to have to flow 10 feet before it reads it, which is going to create some problems. Another case is when you have a high order process, and it just takes long enough for that data to actually collect, or to actually read out. And that's a lot of the times what we deal with as chemical engineers. How do we model this? The easy way to model here, we're going to go over here. This is backwards right now. Hopefully I can spin it around. But in the Laplace domain, it's e to the negative tau s is how I model it. And tau is how long it takes. So if it takes 10 seconds to go, then tau is 10 seconds. Here's our transfer function that we would use to measure it. It's just like the original transfer function is equal to the new transfer function times the e to the tau s. In the time domain, which you have to take the inverse Laplace transform of this, which ends up being this. Just kind of crazy, so we don't really do it. We have something else do it for us. Thank you.